equilibrium between two phases of a pure substance. As another example of this requirement for equilibrium, let us consider the equilibrium between two phases of a pure substance. Consider a control mass consists of two phases of a pure substance at equilibrium. A control mass consisting of two phases of a pure substance at equilibrium. We know that under these conditions, the two phases are at the same pressure and temperature with same T and P. Consider the change of state associated with transfer of dN moles from change of state transfer dN moles from phase 1 to phase 2. While the temperature and pressure remain constant. So we have T and at stage 1. The Gibbs function of this control mass Tp n1 n2 where n1 and n2 designated the number of moles in each phase. By definition, we can calculate that Gibbs function constant. Therefore, at constant temperature and pressure, we can write this relation. Now, at equilibrium, D therefore at equilibrium we can write at state 2, that is under equilibrium condition, the Gibbs function at each phase of a pure substance is equal. Let us check this by determining the Gibbs function of saturated liquid and saturated vapor from the steam table. For example, the Gibbs function of saturated liquid and saturated vapor saturated liquid and saturated vapor at GF for liquid, HF minus T, SF. For vapor, G for gas, TSG. Equation dg Gibbs function equilibrium d, g, t and p equation. This can also be derived by applying the relation TdS dH minus VdP to the change of the phase that takes place at constant pressure and temperature. Constant T and P, we have this relation T ds equals to dH. We make an integration from change to change phase. Integration from fluid to gas TdS dH. TSGSF The Clapeyron equation, which was derived before, can be derived by an alternate method by considering the fact that the Gibbs functions of two phases in equilibrium are equal. In the Chapter 14, we consider the relation for a simple compressible substance that for a simple compressible substance dG Consider a control mass that consists of a saturated liquid and a saturated vapor in equilibrium, and let the system undergo a change of pressure dP. The corresponding change in temperature as determined from the vapor pressure curve is dT. Both phases will undergo the change in Gibbs function dG, but since the phases always have the same value of the Gibbs function when they are in equilibrium, it follows that dG yani gas with combining these two relations, dGF VF dP SF dt, and dG for gas and since we have the GF, we can count this relation DFG DGG. It follows that EF dP minus SF dt VG minus SF dsG. dt. dpbg minus df dt sgsf. In summary, when different phases of a pure substance are in equilibrium, each phase has the same value of Gibbs function per unit mass. This fact is relevant to different solid phases of a pure substance and is important in metallurgical application of thermodynamics. There are various examples in this chapter available in the solution video.